In this video, we will work out some colligative properties problems. This video is meant to be watched after the previous video about colligative properties concepts. Please watch this previous video now if you have not done so, or some of the concepts discussed in the video will be confusing. Which has a higher vapor pressure, ethanol, which has a boiling point of 74.8 degrees Celsius, or water? This is a question we pondered in the previous colligative properties concepts video. The definition of boiling point is the temperature at which vapor pressure equals 1 atmosphere. Ethanol's boiling point is 74.8 degrees Celsius, and water's boiling point is 100.0 degrees Celsius. If we draw a graph of vapor pressure versus temperature, and we plot both ethanol's and water's boiling temperature versus 1 atmosphere, you will see that ethanol has a higher vapor pressure. This makes sense because ethanol will boil faster and will change into more vapor at a higher rate than water. This is because ethanol has lower intermolecular forces than water, as water has 2 spots for hydrogen bonding and ethanol only has 1. What is the change in vapor pressure when 164 grams of glycerin, C3H8O3, is added to 338 milliliters of H2O at 39.8 degrees Celsius? The vapor pressure of pure H2O at 39.8 degrees Celsius is 54.74 torr. The density of H2O at 39.8 degrees Celsius is 0.992 grams per milliliter. First, what are they asking us for? A change in vapor pressure when a non-ionic solute is added to water. What do they give us to solve for this? They give us a mass of the solute and the volume of the solvent. They give us a temperature and the vapor pressure of the pure solvent and the density of the solvent. What do you need to know to solve for the answer? Vapor pressure is calculated by Raoult's law, which states that the vapor pressure of a solution is the product of the mole fraction of the solvent and the vapor pressure of the pure component or the solvent. So we already know the vapor pressure of the pure component, the water. It is 54.74 torr. Now we need to calculate the mole fraction of the water, which is going to be the moles of the water divided by the total moles of the solution. To do that, first calculate the moles of water, and then we will calculate the moles of the glycerin, which is the solute. To calculate the moles of water, we start with what we know about the water, which is the number of milliliters of water. What do we need to convert this to get it close to moles? Well, we know the molar mass of water, 18.02 grams per mole. So if we can get the milliliters into grams, we'll be one step closer. But how to get the milliliters into grams? They give us a density of water. To convert milliliters into grams, we need to multiply by the density, 338 milliliters times 0.992 grams per milliliter equals 335.3 grams of water. Now to convert it to moles, we divide by the molar mass. 335.3 grams divided by 18.02 grams per mole equals 18.61 moles of water. But now we also need to calculate the moles of glycerin, the solute. To do this, they gave you an amount of grams of glycerin and a molecular formula of glycerin. First, we need to calculate the molar mass of glycerin. Carbon has an atomic weight of 12.01, and there are 3 of them. Hydrogen has an atomic weight of 1.008, and there are 8 of them. And oxygen has an atomic weight of 16.00, and there are 3 of them. This equals a molar mass of 92.094 grams per mole for glycerin. Now take the amount of grams of glycerin they give you and divide by the molar mass. 164 grams divided by 92.094 grams per mole equals 1.781 moles. Now to calculate the mole fraction of the solvent. Take the moles of water, 18.61 moles, and divide it by the sum of the moles of the solvent and the solute, 18.61 moles plus 1.781 moles, which equals 20.39 moles. The mole fraction comes out to 0.9127. Now, to find the new vapor pressure of the solution, multiply the mole fraction of the solvent times the vapor pressure of the solvent. 0.9127 times 54.74 torr equals 50.0 torr to 3 significant figures. So the vapor pressure is lowered by 4.74 torr. What is the boiling point of seawater? Assume that the average concentration of salt in seawater is 0.560 mole NaCl per kilogram. The Kb value of the boiling point constant for water is 0.52 degrees Celsius per molal, and the NaCl dissociates into two different ions. This question asks for the boiling point of seawater. What is the boiling point of pure water? This is just common knowledge, but we did cover it in the first colligative properties video. Please watch this video now if you have not done so before. The boiling point of pure water is 100.0 degrees Celsius. So to calculate the boiling point of seawater, we need to calculate the boiling temperature change, which equals the Van Hoff factor times the molality of the solute times Kb, and add it to the boiling point of pure water. The Van Hoff factor for the solution of NaCl is 2 because the problem says that the NaCl dissociates into two different ions. To calculate the molality of the NaCl, we need to remember the definition of molality, which is moles of solute divided by kilograms of solvent. The number they have given us, 0.560 mole NaCl per kilogram, is per kilograms of solution. Let's make a plan to convert the kilograms of solution to kilograms of solvent. The only difference in the kilograms of solution to solvent is that the solute is added in there. So we need to subtract the solute from the solution to equal the solvent. Let's assume 1 kilogram of solution. Then we have 0.560 moles of solute or NaCl. We will convert the moles of NaCl to kilograms of NaCl, and then subtract from our 1 kilogram of solution. To convert from moles of NaCl to kilograms of NaCl, first go through the grams by multiplying the molar mass of NaCl. The molar mass of NaCl is 22.99 for 1 Na and 35.45 for 1 Cl, which equals 58.44 grams per mole. Take the 0.560 moles and multiply by 58.44 grams per mole, which equals 32.73 grams. Then divide by 1,000 to convert the grams to kilograms. 32.73 grams equals 0.03273 kilograms. To find the kilograms of solvent, take the kilograms of solution and subtract the kilograms of solute. Remember, this can be done because of the law of conservation of mass. 1 kilogram minus 0.03273 kilograms equals 0.9673 kilograms. Now, to find the molality of the NaCl, take the number of moles of NaCl and divide by the kilograms of solvent. 0.560 moles divided by 0.9673 kilograms equals 0.579 molal. To find the change in boiling temperature, multiply the Van Hoff factor times the molality times the Kb constant. 2 times 0.579 molal times 0.52 degrees Celsius per molal equals 0.60 degrees Celsius. The boiling point of seawater is then 100.0 degrees Celsius plus 0.60 degrees Celsius, which equals 100.60 degrees Celsius. The freezing point of a solution that contains 1.00 grams of a molecular unknown compound, A, dissolved in 10.0 grams of benzene, is found to be 2.07 degrees Celsius. The freezing point of pure benzene is 5.48 degrees Celsius. The molal freezing point depression constant of benzene is 5.12 degrees Celsius per molal. What is the molecular weight of the unknown compound? In this question, they are asking you to find the molecular weight of the unknown compound, and they give you the mass of the unknown compound, the mass of benzene, and the freezing points of both solutions. The units of molecular weight are grams per mole. We already know our grams of solute, so all we need to calculate is our moles of solute. This is a freezing point depression question. The equation to solve this problem is related to the boiling point equation. The change in freezing temperature equals the Van Hoff factor times the molality of the solution times the Kf constant of the solvent. The Kf constant is also given for this problem. We can also calculate the change in freezing temperature when we add the unknown solute to the benzene solvent. The freezing point of pure benzene is 5.48 degrees Celsius, and the freezing point when the unknown solute is added is 2.07 degrees Celsius. The change in freezing temperature is 5.8 degrees Celsius minus 2.07 degrees Celsius, which equals 3.41 degrees Celsius. The Van Hoff factor for the unknown solute is 1 because it is a molecular compound which will not dissociate in water. Now we can calculate the molality of the solute. 3.41 degrees Celsius equals 1 times our unknown molality times 5.12 degrees Celsius per molal. Our unknown molality then equals 3.41 degrees Celsius divided by 1 times 5.12 degrees Celsius per molal, which equals 0.6660 molal. So now we know that we have 0.6660 moles of solute per every 1 kilogram or 1,000 grams of solvent. But we only have 10.0 grams of solvent, so 0.6660 moles divided by 1,000 grams times 10.0 grams, which equals 0.006660 moles of solute. Since we know we have 1.00 grams of solute, now divide this by the number of moles. 1.00 grams divided by 0.006660 moles equals 150 grams per mole rounded to 3 significant figures. The freezing point depression of a 0.10 molal solution of HF aqueous solution is negative 0.201 degrees Celsius. Calculate the percent dissociation of an aqueous HF. This question asks for the percent dissociation of an HF solution. HF is a molecular acid, which means it will partially dissociate in water. So this question is asking us to find the Van Hoff factor for this acid. The equation to solve this question is change in freezing point equals the Van Hoff factor times the molality of the solution times the Kf, a constant for the solvent. The value of Kf for water was given in the previous colligative properties video. Please watch this video now if you have not done so before. To refresh your memory though, the freezing point depression constant for water is 1.86 degrees Celsius per molal. The change in freezing temperature is 0.0 degrees Celsius, which is the freezing temperature of pure water, minus negative 0.201 degrees Celsius. This equals 0.201 degrees Celsius. 0.201 degrees Celsius equals our unknown Van Hoff constant times 0.10 molal times 1.86 degrees Celsius per molal. Our unknown Van Hoff constant equals 0.201 degrees Celsius divided by 1.86 degrees Celsius per molal times 0.10 molal, which equals 1.08, which means the HF is about 8% dissociated. A solution is prepared by dissolving 35.0 grams of hemoglobin in enough water to make 1.00 liters in volume. The osmotic pressure of the solution is found to be 10.0 millimeters of mercury at 25.0 degrees Celsius. Calculate the molar mass of hemoglobin. The question is asking you for the molar mass of hemoglobin, which is a molecular solute, so the Van Hoff factor is going to be 1. They give you the amount of grams per hemoglobin. Remember the units of molar mass are grams per mole. So now all we need to calculate are the moles of hemoglobin. They also give you a volume of solution, an osmotic pressure in millimeters of mercury, and a temperature. The equation you need to solve this problem is the osmotic pressure equals the Van Hoff factor times the molarity of the solute times the gas constant times the temperature at which the experiment is being run. First, let's talk about units. The gas constant has a value of 0.08206 liters times atmospheres per mole times Kelvin. So therefore, osmotic pressure needs to be in atmospheres. To convert 10.0 millimeters of mercury to atmospheres, we use the conversion factor of 1 atmosphere equals 760 millimeters of mercury. So we have 10.0 millimeters of mercury divided by 760 equals 0.0132 atmosphere, which is the osmotic pressure. The temperature needs to be in Kelvin, so 25.0 degrees Celsius plus 273.15 equals 298.15 Kelvin. So we need to solve for the molarity of the solution. Rearrange the equation to solve for molarity. Molarity equals the osmotic pressure divided by the Van Hoff factor times the gas constant times temperature. Plug the values in to solve for molarity. Molarity equals 0.0132 atmosphere divided by 0.08206 liters times atmospheres per mole times Kelvin times 298.15 Kelvin, which equals 0.000538 molar. Since we have 1.00 liter of solution, this means we have 0.000538 moles of hemoglobin. So our molar mass is 35.0 grams divided by 0.000538 moles, which equals 65,056 grams per mole, or 6.51 times 10 to the fourth grams per mole.